Bonjour, je m'appelle Edson Yanaga, je suis brésilien, mais mon grand-parents sont japonais. J'ai étudié un an de français, mais je ne parle pas français. Excusez-moi, pardonnez-moi, je vais parler l'anglais. And that was everything I had to talk to you, okay? Thank you very much. It's my first time here in France and in Paris too. Has been a wonderful week so far. And it's going to be more amazing because now I'll be able to join you on this great developer conference, which is the Vox France. And today I'll be talking about migrating to microservices databases because I've been talking about this subject about microservices for about 3 years now. But every time I give a talk about microservices, the number one question that always arises is, I have to break up my monolith, but I still might have my old legacy relational database with lots of tables and columns. How do I split that into a microservice database? So I decided to study this subject. And for the last 18 months, I've been able to talk to a lot of developers and different teams worldwide. And I think I've been able to collect some techniques that I hope that will be useful for you. So I'm currently a director of developer experience at Red Hat. My Twitter handle is @Yanaga. And I'm also a Java champion and a Microsoft MVP, which I know is kind of weird combination. But just to show you how the world is changing after all. Really? Yeah, because I've always been an open source advocate, so now it's very good to see that in the end, open source won. Because even the largest proprietary software company in the world now has bent their knees to open source. It means that we've been doing something good for the past years. And I also like to just give a hint to you. I've just published a book from O'Reilly with the subject of this talk, which is Migrating to Microservice Databases. It's available for now for free at the developers.redhat.com site. You don't have to type everything. If you just go to the website, you'll be able to download the book for free. And we still have some very few copies left at the Red Hat booth. So if you want to hurry after the session, try to pick some of the books. There might be some available. And if anybody got a hard copy, I might be able, if you wish, of course, to sign them too later at the booth. But I'll be here sticking around until tomorrow, okay? So that's my tip. So at least for now, it's available for free at the developers.redhat.com site. And I always like to start my talks with this quote from Forbes that now every company is a software company. I like to say that you don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company because software is changing the world. And with all of these new things that we're calling digital economy, we have some great examples of these companies, like the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. Questionable content, but it is. And all of these companies, they have something in common, is that they are all enabled and they only exist because of software. So software is changing the world. And we all know that as we software developers, I always like to introduce myself also as a software craftsman. And one of the best definitions of a software craftsman that I have is that a craftsman is somebody who cares about his job. And we know that software can change people's lives for the better. And we know also that we can make people miserable with the software that we do. So I made a choice some years ago. I decided that I wanted to make people's lives better with the software that I produce. And I also decided to try to help other developers worldwide to try to create better software. So I believe that if all of you are here today at such an important conference as DevOps to try to learn something new, I know that you care. So I wish that we can all decide to make a choice to improve people's lives for the better with the software that we make every single day, right? And on this journey, thank you. And all of this journey that we're deciding to deliver better software into production, we've been talking about DevOps on the past like 5 or 6 years, and microservices in the past like at least 2 to 3 years. And there's a lot of content about these two subjects, DevOps and microservices, but I had to choose just one thing. So if I had to tell you just one thing about DevOps and microservices, is that all of this culture, all of this movement, they only exist because we want to improve something that we call the feedback loop in the software development process, which means that we need to deliver things faster into production so we can shorten our feedback loop, so we can improve the quality of the input that we receive from the feedback loop. You see, the faster we deploy things into production, the best is the software that we deploy to users. You mean because sometimes if you're doing something and you take like 6 months to deliver that into production, I once heard a case yesterday that there is a company, obviously I won't be able to say names, but they take 4 years to release a version into production. 4 years. Yeah. Imagine you're coding today, and the software that you're coding today will be deployed into production 4 years later. Yeah? You won't even remember what you did 4 years ago. Okay? And if something went wrong, obviously you don't know, because lots of people, hundreds of people, millions of lines of code were written in the past 4 years, and when you deploy that in production, if anything goes wrong, you have absolutely no idea of what went wrong between the coding and the release to production. That's why we need to shorten this cycle. And imagine, and technically, the term that I have to present to you in the DevOps world is called the batch size. The batch size is the amount of things that you deliver in each one of the releases into production. So if we were able to reduce constantly our batch size until we can reach like the ideal, perhaps ideal size of 1 commit, 1 deployment. If you're coding here and you just type it like 50 lines or 15 lines of code, and you deploy that 15 lines of code into production, if anything went wrong, where's the problem? In that single 15 lines of code that you have into production. Okay? So reducing constantly our batch size is not only the best way to improve our feedback loop, but is also the safest way to deploy software into production. That's why we constantly need to aim to reduce the batch size of our releases. But even if we try to reduce constantly our batch size, because that's the most important thing that you have to remember about DevOps and microservices, we're trying to reduce our batch size. In most of the organizations, we have something called a maintenance window, which is that specific time of the day or the month or the year, for some companies, that you're able to deploy software into production. Why is that? Because you're not allowed to disrupt users into production. You can't go in the middle of the day and say, oh, I have to release a new version of the software. There are currently like 5,000 users using that at the moment. I just have to drop them, have them wait like 30 minutes, and it will come back, hopefully. You're not allowed to do that. And that's why the ops guys, usually they say to you, oh, you're only allowed to deploy new releases of software Saturday, 3 a.m. In the morning. So, of course, you don't want to do that. That's why you leave the things to be deployed by the ops guy. And that's another discussion we can have another day. But you see, the maintenance windows prevents you from deploying software into production faster. The maintenance windows prevents you from reducing further your batch size. So if you want to have a smaller batch size than the maintenance window time, you need something that we call zero downtime. You need some way to deliver software into production without disrupting your users. And I'll explain to you very quickly the single requirements that you need for a zero downtime deployment. In fact, it's not the single requirement, it's the first requirement for zero downtime deployment is for you to have a blue-green deployment. What is that? Blue-green deployment, in a traditional deployment, you have like your clients issuing requests directly to your servers, your deployment service. And then if you want to have blue-green deployments, you need to add another component to your architecture, which is the proxy, which can be a reverse proxy, which can be a load balancer. It doesn't matter. We have a lot of different software being able to do that. I'm just calling proxy because it's something between your clients and your deployments. When you add a proxy, which is routing our requests between clients and deployments, now you can add another deployment. Now we have 2 different environments, blue and green. Each one of them is capable of handling 100% of requests, production requests at a given moment. So you have a copy of your deployment, a blue deployment and a green deployment, both running at the same time. And if I want to release a new version of my software, what do? I just ask the router to stop issuing requests to my green deployment. Then I get stop the green server. I copy the new artifacts. I start the server. Maybe I have some time to wait for them to warm up. If we're Java developers, we know that application servers, sometimes they take some time to warm up. We wait for it to be ready, hot. When everything is OK, then we can ask the proxy to start routing the request back to the green. And then we do the same process with the blue deployment. We stop, we copy the artifacts, we start it up, we wait for them to warm up. Then when everything is OK, we can ask the proxy to route the request back again to the blue. You can see the blue or the green deployment as a standby environment, or even better, you can use them to load balance your requests. Maybe you're able to, in a peak moment, you may be able to handle much more requests because now you have twice the capacity that you had before. It's not exactly twice because we know that we have some contention, but you're improving your capacity to handle requests with this kind of deployment. And you have zero downtime. But you may ask, like we're talking about relations databases, aren't we? So when we're trying to do zero downtime deployments with codes, it's pretty easy. I'm not saying the code is easy. We know especially that crafting good code is particularly hard. But no matter how hard is your code, state is always harder. And when I say state, we have two different kinds of states in our application. Well, at least two. And one is ephemeral state, which is the kind of state that you usually store in this HTTP session of your web server. And the other one is persistent state. With ephemeral states, it's not unusual for you to discard the information. But if the user was typing something, the worst case scenario, he lost everything that he was typing and he has started over. But with persistent states, you're not allowed to lose any kind of information, such as the information that you're storing in the database. So the question is, how do I apply zero downtime deployments if I have something that is stateful, such a relational database? So that's the question that I want to try to answer today. What about my relational database? And the answer is how do I say? It's simple, but it's not easy because you have to change the way that you think about database deployments. But the first step for that, you need to automate all of your database migrations. And I'll tell you, technically speaking, if you're talking about a relational database, the state of the structure of information is called a schema. And when you change the structure of the database from one schema to the other, the things that you do to change the schema from one state to the other, these things are called migrations. Okay, so migrations is the amount of change that you apply on a schema from one version to the other. And you need to automate this migration, so we have some database migration automation tools. The two most popular ones in the Java world are Liquibase and Flyway. Liquibase is a bit older. I know they are both now feature complete. They're almost feature compatible. I have a particular preference for Flyway just because I've been using Flyway lately. And because also in one of the latest projects that I developed before joining Red Hat, I used Flyway to apply my database migrations both on the server and on Android databases. So Android has a SQLite database, and I was able to modify a bit the SQL Droid, which is a JDBC driver for Android, and I deployed that to Maven Central. So now it's working on Android too. And it worked successfully on my last Android project. So that's why I chose Flyway, but you can choose any of them because now they almost have the same set of features, and they're being used successfully into production in many different companies. So first step, you have to automate everything. You're not allowed to get your SQL scripts for the new version and email that to your DBA to be applied on the weekend. No more. They are going to be applied automatically, either by your software, your code, or either by your software deployment pipeline. Okay, These are the two most popular approaches. I particularly prefer them to be deployed through your software deployment pipeline. Usually you add a step on Jenkins or any other continuous integration server for doing that. But you can also use automatic migrations when an application starts up. Okay, it's up to you to make the choice. And the answer, so if I want to apply zero downtime releases to my software, I also need some zero downtime migrations, because you're not allowed to alter table something in your production database between one version and the other. So the answer for that is that your versions of both codes and database must from now on be back and forward compatible, because since we're having blue-green deployments, it's possible and very likely for you that you will have two different versions running into production at the same time. So your both versions, database and code, must be back and forward compatible. You must imagine that in code, again, it's easier, but with state is much harder. And the answer for that, how do you apply zero downtime migrations on relations database, is that first, you're not allowed to have long SQL scripts anymore. You have to apply babe steps, which means that each one of our migrations will have the smallest possible batch size, which means that for most, if not all use cases, all of your database migration scripts will have only one single SQL script. Okay, no more lots of scripts, just one. And if you have to update any kind of data inside your database, if you have to copy the data from one column or table to the other, if you have to update something, if your table has too many rows, you're not allowed to do that update table something, set something to something, and that statement locks your database for 5 minutes. It's not allowed anymore, because this 5 minutes means lock time, and lock time in a database means downtime to your users. So you're not allowed to do that anymore. And the answer is, if we have we have big tables with long lock times, then we need to shard our updates. And sharding is a very fancy word in the database world, just to say that you have to split your changes. If you have like 1 billion rows in your table, now you will only be able to update like 1,000 for each one of these update statements, and which means also that each one of your new versions of software will only update like 1,000 rows in each one of these releases. So you might be wondering, does it mean that I'm going to deploy a new version to production just to update 1,000 rows? Yes. And it might seem a lot of work if you're doing it manually. But if it's automated, it's just a matter of committing a line into your repository. Okay? Yeah? That's how most companies do these days that are applying zero downtime migrations. Okay? So instead of doing just alter tables, customers rename something to something, then maybe you have to refactor this database migration script to a lot of different statements. So maybe now, instead of just renaming, you have to add a column, then you have to copy the data from one version to the other using shards, which means that first 100, then 101 to 200, and then everything goes. Then in the end, if everything went well, the production code is running gracefully in the past 2 weeks, then you're able to delete the column. Okay? So I collected from many different teams worldwide. The most common scenarios are these 4. For zero downtime migrations, trying to add a column, rename a column, change the type format of a column, and deleting a column. You see, I don't have migrations for tables, but if you see a table as a set of columns, it's easy for you to apply the same steps for a lot of different columns on tables. So I'm going to show you now very quickly which are these steps. And the first migration is add a column. Each one of these numbers, 1, 2, 3, and 4, is going to be a different release of your software. So if you do that, each one of your versions will be back and forward compatible between consecutive releases. So the first version of your application, you just add a column, and you don't use that yet. The second version, you deploy a new version, your code computes the read value. Computing the read value means that either you choose a default value, or you can calculate the column value through other columns in your other data from your database. So you just compute the read value and write to the new column. Okay. Then between each one of these steps, you can open your database CLI. You can issue the select statements to check, is my application writing the data correctly to the database? Okay, is it computing correctly? Is the structure of the schema correct? So you can check your database between each one of these steps. That's why it's so safe to deploy migrations this way. On the third step, you update your data using shards. You copy the data from one column. Yeah, you might update the values if you can compute that, or you might issue an update statement to a default value. It depends on your use case. You update the data using shards, and on the last step, your code reads and writes from the new column. Okay, so just to add a column in your database, you apply 4 different consecutive migrations to your database, and between, if you do that on these 4 steps, each one of your database versions and the application too are back and forward compatible. So this is very safe for you to deploy into production because you never issue a destructive statement to your database. Your database is always there. You can always roll back to the previous version and it will still be running. That's why it's so safe. Okay, but adding a column is kind of simple. The hardest migration, well, the one with most steps is rename a column. So if you want to rename a column, you have to apply at least the 6 steps, which means that the first version adds a new column. The second version, the code reads from the old column and writes to both. Third version, you copy the data using small shards, and you can guess if you're sharding, you can have multiple releases on the step. Fourth step, code reads from the new column and writes to both. Fifth step, code reads and writes from the new column. And if everything is going well, you're pretty sure that you're not going to need the old value anymore from the column. You can mark the column for deletion later. When do you do that? On the maintenance window. You just now you open a ticket on your Jira, and you ask the DBA for, oh, now you can schedule the column to be deleted on your next schedule maintenance. So why you don't do that immediately after applying your new version? Because deleting a column is the destructive statement. If you delete it, you lose the data. The only way to recover it is restoring a backup. And you don't want to do that into production. Of course, we all have like horror stories. I had to do it once into production. But the problem is that restoring a database took 12 hours. So it's not a fast thing. And we lost the data from the new rows anyway. So it wasn't a pleasant day. Okay. So the next migration is change type and format of a column. And can you see a pattern here? Rename a column and change type format of column. These are exactly the same steps that you apply if you want to do a zero downtime migration. And that's a good thing, because if you take the habit of rehearsing these database migrations into your code, then you realize that it's always the same thing. You always apply the same single steps. And I have to give you an advice. You don't just commit and deploy that. You have to rehearse these migrations using your data. So you're going to rehearse because dealing with data is extremely dangerous. So even if they're safe, you're going to rehearse these migrations up to exhaustion, first on your development machine, then in your testing environment, then your QA environment, before deploying that into production, because you want to play on the safe side. Okay? And the last one, deleting a column. No, you don't delete a column. Yeah, you never delete a column. Why? Because that's a destructive statement. So you never delete a column. You just stop using the read value, but keep writing to the column. Until when? Until you decide, I'm pretty sure this change was done like 3 months ago or 1 month ago, depends on your business case. I'm pretty sure I don't need the data anymore. Then you can ask the DBA to delete the column. And of course, you have to stop using the writing to the column too before doing that. But that's basically the thing. You don't delete a column, right? Then somebody might ask, what about my referential integrity constraints? If you think about constraints, it's a safety net that you use so that you don't insert invalid data to your database. And I know that the simple answer for that is that sometimes you have to break some walls to make room for improvements. So you have to drop them and just recreate them when everything's okay. And I know that I'm suggesting you to drop the safety net of your application exactly when things are more likely to go wrong, but you don't have a choice, right? You have to change. Then you can recreate them after everything is doing fine. So that was the part about zero downtime migrations. Now we have to talk about splitting and integrating our microservices database using particularly relational databases. So when we're talking about microservices, Martin Fowler collected a bit of microservice characteristics. These are the 9 most important ones. I've decided to choose just one, decentralized data management, which is the subject of this talk. And that's why we have to talk about extracting your microservice database. The decentralized data management principle states that we must have one database per microservice, right? Each microservice must own its own data, so we must have one separate database per microservice. But then the question is, but I have a huge legacy, monolithic database. How do I split it, and how do I integrate it later? Okay, splitting, in fact, is probably the easiest part. I'm not saying easiest, the simplest part. Yeah? But splitting the database is not easy because it's a state of information. You have a lot of tables and columns and relationships between them. For you to be able to identify which part of your database are you going to split, you have to apply some techniques. Probably one of the most important ones is domain-driven design, for you to figure out which parts have a different life cycle inside your application architecture. I won't be able to cover that, but after you have decided which tables and columns you decide to split, then I'm able to tell you how your application will continue to work after you decide to split that database. Okay? So, if I want to split an old legacy monolithic database, it means that for a given amount of time, it depends again on your use case, both your monolith and your new microservice, they will have to read and write information from the same database. Then you might be able later to choose another integration technique to be able to spread information between your system. And that's what we're going to discuss now. So splitting is not easy, but how do I integrate later? And before I introduce you to some integration techniques, I have to start a discussion about consistency models. And I know this is a hard subject for anybody that ever tried to study distributed systems. So I've just chosen 2 different consistency models, which are kind of simple. But there are other ones that we're going to use, at least in our use case. We can have strong consistency and eventual consistency. And for those of you that are not aware of these consistency models, strong consistency means that if I have like different nodes in my distributed systems, which is the case if I have a monolith and many microservices, all of the nodes in my system, they must agree with the new value before exposing the new value to the clients, okay? If I say here, A is equal to 5, everybody in the system has to agree, okay, A is equal to 5 before anybody can read the 5 value, right? That's a strong consistency model, and that's usually what we can achieve when we're using distributed transactions, right? Eventual consistency in the other way, and particularly, I'm going to talk about strong eventual consistency. Which is the use case that we have when we're dealing with this kind of enterprise integration. Strong eventual consistency, or to shorten that, eventual consistency in our particular case means that one of the nodes will be the canonical source of information, because if I decide to split the customer table or the customer information from my monolith into a separate database, it makes sense for me that the only artifact of my system that will be able to change the information of the customer is the microservice customer, right? So we have a canonical source of information. That makes our model much simpler. So I have a microservice, a customer microservice. It is the canonical source of information. So the only node in the system that is allowed to change the customer information is here, which means that I can update the information here. But if I have an eventual consistent system, the other nodes, they can have outdated values, but that's correct information, it's just outdated. How much outdated depends on your business case. It can be 1 microsecond, 5 seconds, 1 hour, 1 day, depends on which integration technique that you use and what do you need for your system, okay? But if you think about it, my system can't handle eventual consistency, okay? I need a strong consistency. Think again. Most of the use cases that we have in the real world are already eventual consistency. Even if you're reading, you have a web page, you're using transactions to read information from the database, and you display that to your user. When that information left the transaction, it's already outdated. What you're seeing is not the current information, but the information as it was some milliseconds ago, or if you leave the page stale for some minutes, it's the information that was like there 5 minutes ago. So most of the use cases that we have in the real world are already eventually consistent. So you have to think carefully. Maybe you can model your system to handle eventual consistency. Even that reports, every time that you print a report is already an outdated information. And I know that many business people, they like to have their printed reports on top of their table at the morning, generated by some sort of tool like a ClickView or Pentaho. You know that that information is from the last night. They're taking business decisions based on outdated information, okay? That's the real-world use case for eventual consistency. And we have to handle with that, okay? We have to deal with that. And I have to talk about CQRS and CRUD too. I'm going to give you a very quick explanation because many people have different notions of what is CQRS, and some of these notions are wrong on the internet. That's why I decided to discuss that too. So let's start with CRUD, which is architecture that everybody knows, at least I believe that everybody is used to. CRUD stands for create, read, update, and delete. And when you use a CRUD, particularly in the case of database, means that you have all of the 4 operations, the read and write operations. You're using the same data model, which in Java means that you're using the same set of classes, and the same set of tables and columns for both read and write operations. Okay, that's the most common architecture and also the most efficient for simple use case. But if you have, now we can have another kind of architecture, which you just didn't know that it had this name, which is CQRS, which means that we can have different sets of classes for the read and for the write model. What is that? Maybe you want to store the information from the customer using the customer class. But when you want to display the information to the user, you don't want to retrieve from the database a customer and an address and a phone and everything else. No, you just create a DTO with the aggregate information from all of these tables and columns, because the only thing that you need to show the user when he needs a transaction report is just the name and the current phone number of the user. Maybe that's the information. So instead of retrieving all of these entities from your database, you decide to create a DTO, and you create a query, and the only thing that you return from the database is the customer name and the phone number. Okay? You're using a different model to write information, and you're using another model to read information. That's CQRS, okay? When you use different models from write and reading, okay? And you're used to do that because sometimes, in most enterprise systems, we have this kind of complicated reports. We're used to do create materialized views that automatically aggregate information that we want to present the user just for performance reasons. That's an application of CQRS. So if you have a different set of tables, in this case, you can have a different set of classes in your code, or you can have different set of tables and columns for reading information. That's CQRS. It depends on the level that you're applying the CQRS. So when you realize the CQRS is just that, you're just using different read and write models for your application, you realize that you're not tied to have just a single data store. You can have more than one data store. So if you're using CQRS, you can have one write data store, and you can have a read data store. Like I said, you can have one set of tables and columns for writing, and another set of tables and columns for reading. And if these tables and columns are already separate, what prevents you from getting this read database into another database? Okay? You see, if you start to apply CQRS in your concepts, then splitting maybe becomes easier. Integrating also becomes easier. That's why we're talking about CQRS, and that's true, because when everybody starts to think about, oh, I'm going to split my monolith into microservices, then I say, oh, I extracted the customer information here. It's on a separate microservice. Everything I have to do is I'll just change my DAOs from my monolith. Instead of issuing queries to my database, now I'll just create a REST endpoint here and issue a network call to retrieve information. You deploy that in production, you realize that fails miserably because it simply doesn't scale. Okay? So you have to you need other ways to have the customer information back on your monolith, because for performance reasons, just in this use case, REST works for some use cases, but most enterprise software, it doesn't handle very well these use cases. So you need some kind of the customer information cached here or replicated here. So you have the write data store on your customer microservice, but you have the read data store inside your monolith, because you need the customer information for almost everything in your system. You're not allowed to use REST endpoints for doing that. You can have a REST endpoint, but for sure, the monolith won't consume the customer information from that REST endpoint directly. Okay, and I also have to talk about CQRS and event sourcing, because I've seen many people discussing event sourcing as it was like a silver bullet for solving integration problems in distributed systems in microservice architecture. And I'll tell you, event sourcing is very hard to do it right. I've visited many different teams worldwide, and usually when people try to do event sourcing, they do it wrong. Is it even worse than having an entangled monolith is doing event sourcing wrong, because now you have to maintain tightly coupled systems with different artifacts, because on your monolith you can refactor with your IDE. If you have tight coupling between distributed artifacts, you have different code bases. It's very, very hard for you to refactor these things later. So if you want to know event sourcing is another very fancy name to say to you that the state of the data is not a column in the database. You see the classical example, the bank account. If you have event sourcing, the state of the data, how much money you have in your bank account, is not a column in the system. What is that? If all of the bank accounts start with a 0, if you apply credit and debit statements, transactions to my bank account, then state information, what is that? I take the 0 and apply the debit and credit successfully until I have the current amount, right? That's event sourcing. But guess what? It doesn't perform very well, because if you have many bank accounts and many transactions, it becomes to be very slow to have the current amount of money that you have in each one of these bank accounts. That's why usually you create another table, or you create another column in another table, holding the bank account ID and the current amount of money that you have that. But this column is not the canonical source information, it's just a cache for performance reasons. And then you realize that the separate table could be created by a view, or could be created by a materialized view, or could be computed in another way. So that's a classical application of CQRS. If you have event sourcing, usually you apply CQRS too, because you need that for performance reasons, right? But most of us have been doing this for some times in enterprise software. So now that I've explained these concepts, I can show you some integration scenarios that I've collected, which are shared tables, database view, database materialized view, triggers, transactional code, ETL, data virtualization, event sourcing, and change data capture. Okay, that's the scenarios that I'll have to cover to you very quickly, because I don't have much time, but I hope you get the point. You can read the book later too. And shared tables is the fastest data integration approach, because it's kind of dirty, because you just create a new artifact and you still read the same tables. You always have strong consistency, because that's the same database and you have transactions on that. But it leads to low cohesion and high coupling, because if you change anything here, you have to change there too. In fact, when you have to change 2 different points just to change one table, then the architects usually decide it's not worth changing at all. Just leave it there and don't touch it, okay? Because or else you have to cascade changes into multiple different artifacts. So usually that's an anti-pattern, but if you choose to do that willingly, if you know that I'm going to do this hack just because I have it now, but I'll know that I have to change this approach later, then it's an option to be considering, okay? Shared tables. Second option is a database view. This is the easiest one to implement, just create view. It has the largest support on the EBMS vendors, because as this year, even embedded database like SQLite and A2, they have support for views, so there's no excuse for not using them. You might have some performance issues depending on your database and how you create your view. You have strong consistency because you're issuing transactions to the same database. One database must be reachable by the other, which means that at least on Oracle, if you have a remote database, you have to create a DB link between them. And I know that many DBAs are going to bash me for this, but I've seen people doing that, and sometimes it works. Okay, you can use a DB link. Yeah, I know they don't like it, but it works. Okay, in some use cases, it works. And again, depending on your database, it's updatable. I know that at least on Oracle, and somebody told me that on SQL Server this is true. Your views can be updatable depending on how you create your view. You also have the option for database materialized view. It has better performance than simple views. You can have stronger or eventual consistency. If you decide to update the materialized view on each one of your commits, then it's stronger consistent. If you decide to update that on a trigger, a timer trigger, or on demand, it's eventual consistent. One database must be reachable by the other again, which means a DB link for some cases. And depending on your database, also it can be updatable. At least I know that at least on Oracle, that's true. Why I'm saying that? Because I know that most enterprise companies are using Oracle or DB2. I don't have experience with DB2, but I know that in Oracle is possible. And database triggers, which means basically code that you put inside your database, depends on DBMS support, because not most, but not all database support triggers. It has a strong consistency because you're dealing inside the same transaction. One database must be reachable by the other. Again, DB link. But I also don't like this approach because which means code, and it's only feasible if you only have one monolith and one microservice artifact, because you only have one endpoint to update. Either you have your microservice and triggers update the monolith, or the other way. If you have more than one microservice, it's impractical, because then you have to cascade the change between multiple databases, maybe using multiple DB links. It doesn't perform, usually it doesn't work, and it's a nightmare to maintain. But it's possible. I've seen people doing that. If you have a simple use case and you know that's temporary, you can use it. Transactional code is kind of the same use case as triggers. When I say code, it can be any code. It can be distributed transactions. It can be store procedures. Again, you have transactions, then you have strong consistency. You might have cohesion and coupling issues because it's code, possible performance issues too, updatable depending on how it's implemented, because it's just code. You can do it however you want. But again, it's pretty impractical if you have more than one microservice in your system, because you have coupling issues and you have cascading changes. And the more endpoints you have, the lower the performance. So if you have too many artifacts, it quickly becomes impractical. ETL tools. ETL tools is some people call it BI tools, business intelligence tools, tools like ClickView and Pentaho, or Dashlane. No, not Dashlane. Dashbuilder. And you have lots of available tools in the market. Usually, it requires an external trigger, which is time-based. You can aggregate from multiple data sources. You have eventual consistency, but it's only a read-only integration because ETL tools are not designed to write back. Data virtualization. I'm going to hurry because I'm running out of time, okay? You have real-time access because you're reading from the real tables beneath the data virtualization platform. You have strong consistency, can aggregate from multiple data sources, and again, it's updatable depending on solution that you choose. I'm showing you the picture of the TEID, which is an open source data virtualization platform. I don't expect you to know what's written there. I just want to show that you can aggregate from multiple different data sources. You can create virtual databases on the middle layer. Then you can have clients, which will be your application on top. And the cool thing about virtual databases is that you don't touch the physical database. And you're deciding which piece of my monolith will I be able to split into a microservice. If you do the physical splitting, it's very hard for you to get on the step back later. But if you're using a virtual database, it's very easy for you to play. Oh, just create a virtual database using these tables here. And let's see, play with the code. It didn't work. You can just throw away the virtual database and start it over. But if it went right, then you get the virtual database and split that to the physical database on that. So virtual database, I think it's one of my favorite approaches because it's also the safest. You can always roll back because you changed nothing in the physical database, right? Event sourcing, which is the silver bullet for many, and I don't like this approach as a silver bullet, because it uses auditing, it has eventual consistency, usually tied to a message bus. Since you use a distributed broker, you have high scalability. But the problem with event sourcing is that you have to change your legacy application to be modeled as events. And if your application is not modeled after that, who wants to touch a legacy code to change for that? Nobody. So you're not going to remodel your system just to do event sourcing. That's why it's not approachable. If you have a greenfield application, perfect. Just take care, because event sourcing is hard, and most people don't realize that. Even they only realize that after they did the mistake of doing. So just take care of that, because it's a wonderful solution if done properly. Okay. And how do you get experience on that? Just doing it wrong. Okay. And change data capture, which is the last integration. You have the read data source. Is updated from. Is my favorite one for legacy systems. And I'm about to change. You change it. You connect to your CDC software to your database. It reads the database transaction log, and for each one of your create, read, delete, create, update, delete, and alter table statements, it creates one event which is propagated through the bus. Then you can read that information and use to update your other endpoints. I suggest you to take a look at this very cool open source project, debezium.io, which is an open source CDC capture. And if I just have to show just one thing, is that I want to, because I won't be able, I have Debezium running on my machine. I just want to show one event. I'm going to insert one user. Oops, you're not seeing that. I'm just going to insert one user into a table into my MySQL database. Debezium captured this event and create an event here, which was propagated on a Kafka bus. And if I show you the event, the cool thing about Debezium is that you know the event. It says before it didn't have anything. After that, this is the information that I have on the database, and the operation was a create. Okay, and Debezium propagates the information for all of the operations that you have on your database, and it also has the current and the previous version of your schema. That's why it's so useful, right? And I'm already too much over time, but that's what I wanted to show you today. I suggest you to join developers.redhat.com, at least to get the book. Yeah, I would love your feedback. My Twitter handle is @Yanaga, and thank you very much. Merci beaucoup.